So a couple of people may have seen this before. I'll be totally honest, I was way too busy in the last couple of weeks to write a new talk. I gave this one at CarolinaCon in Outer Zone, so if you've seen it before, I'm really sorry. If you haven't, then it might be some new material, and that'll be cool. I'm into passwords. Anybody that knows me knows that. And so last year I did a bunch of talks on the technical tools and stuff to crack passwords, but this is more on like profiling password policies. So it's called Your Password Policy Sucks. Oh, hold on. Okay. So everybody does this, so I do too. I do a couple of things. I'm a security consultant for Hack3rcon Labs, like Tim before me and a couple of other guys are here that work from Hack3rcon. I'm also a core developer for Backtrack Linux, if anybody's ever heard of that. I'm a co-founder of a website called QuestionDefense.com, and then I'm also a co-founder of DerbyCon, which is a security conference we had a couple of weeks ago. And the thing I like to put on there that makes me qualified to talk about passwords is that I'm a member of Team Hashcat. 2 years ago, we won the Crack Me If You Can password cracking contest. Last year, we came in second. We were beat out on some extra points technicalities by the Russian people. So first and second is still honorable. I'm not going to talk bad about Russian people. Anyway, and so I always throw this in there. I'm not a password cracking expert. I don't know everything. I'm frequently wrong and slow to admit it. And I'm not responsible, obviously, for what you do with any of this information. All right, so what are we going to cover in here? Why passwords are still a vector of attack. As we all know, everywhere we work and go still uses passwords. A couple of places have gone to two-factor authentication, but the primary method of authentication is still passwords. And we're going to talk about some bad password policies because what makes password cracking so easy at this point is the policies that system administrators, network engineers, and all those people put in place. We're going to look at some recent breaches and what the most common types of passwords were, some advancements in recent password recovery, and then we'll talk a little bit about some tools and techniques. I'm biased to Hashcat, so that's probably all we're going to talk about. All right, so what's wrong with passwords? Like I already said, they're a weak method of authentication. The reason is because we're relying on the human to think of the password. Humans, you know, when you go to the website and you click one of those complexity generator things for your password, that is not easy to remember. And so even if you do that for all your passwords, they still have to be stored somewhere. And it's a pain. So as humans, we make up passwords that we can remember. And so that's what we're going to kind of look at. Many websites still use really, really simple hashing algorithms. I mean, I cannot believe it when I go to a website and they ask me to register and I look at the session token and my password is being hashed in MD5. I mean, it's, in 2011, it's really ridiculous. Like I said already, humans are predictable. I can predict almost to the character set how a human is going to construct their password, and we'll look at that just in a little bit. And so along with all of this stuff, you add GPU recovery onto password cracking, and it just becomes utterly ridiculous how fast we can crack passwords. I think I was on a pen test about a month ago, compromised the domain controller, dumped 7,000 NTLMs from the domain controller, used some custom rule sets of mine, and had cracked 6,000 of them within an hour. And that's using the default Windows AD policy, which is what primarily is in place wherever I go. So I always like to talk about this. If you imagine, like, people could be compiling databases of passwords, right? I mean, all these passwords that are leaked out on the internet every time a website's compromised and they dump all the hashes on the internet, you know, where are those going? What if people are keeping those? And what if they're using those databases to make statistics and word lists and all that kind of stuff? And what if, based on GPU policy, they could load all of those passwords into memory, and they could do really sophisticated attacks, brute force, positional settings, all that type of stuff. So there's really no need to imagine. There's tons and tons of hacker groups that are doing this type of thing immediately. I don't know if anybody's a big Twitterer or anything like that, but if you look on Twitter, whenever a group like LulzSec or Anonymous or one of those types of organizations compromises a website and dumps its database somewhere, there's always a mad scramble to get that database so that the passwords can be cracked. And the reason for that is those are real world passwords. Those are passwords that people are using every day today. And as we always know, if you use a password one place, the chances of you using it another place are really, really good. So there was a time a few years ago when password cracking was kind of on the downward spiral. People were talking about, complexity, 10 characters or more, and then GPU password cracking hit the scene and has made immeasurable strides. We'll look at a few statistics, but sort of a rough one is, John the Ripper can do about 1 million passwords per second, and a couple good ATI GPU cards can do about 5 billion per second. So it's a fairly substantial margin there. So this is one of those databases I was talking about. This is a private one my friends and I keep for security research only. We don't give it out because we don't want this stuff to be used for bad. However, there's other things like this in existence, and the bad guys do have them. And so you can see the way that we classify everything, we have the name of the hack. You'll see some websites on here that you recognized: Airsoft, Blood and Honor, Carter's, DreamHack, eHarmony. I mean, there's a Gawkers, there's a bunch of them. We put the type of algorithm of the hash, how many we've found, how many we've had left, and these are hyperlinks, so you can just download the lists. Then we also have a dictionary you can download of each attack, and then we have an analysis, and we'll look at some of the analysis tools. So this is the kind of sophisticated stuff that people are keeping so that they can attack your websites. So you're saying to yourself, I got a good password policy. And most companies do have some sort of password policy, and unfortunately it can help us as attackers. One thing that I have noticed is that many companies never change the default Windows Active Directory policy, which is a character minimum, 1 upper, and either 1 special or 1 number. And we'll look at why that's not really a good policy. But here's a real world example I found on the internet. I've actually blotted out the name of the company so that they don't get mad at me because this is so ridiculous. So let's look at this password policy. So your password can be any combination of 6 to 10 letters and numbers, right? 10's not very much. A company you should never put a limit on the length of the password policy. So 10 characters isn't very much. What's interesting is that they actually removed special characters. It cannot contain any special characters. So this policy was a web application on the internet. And so what this says to me is that whoever coded this web application was such a shitty developer that they couldn't figure out how to get those characters to sanitize in the username and password field. And so they just left them out totally. So there's a couple more interesting things here. It can't contain your username, that's pretty standard. But this is interesting too. It can't contain 2 separated numbers. So that means that you can have numbers, but they can only be together. They can't be separated. And then it cannot contain, I don't even know who thought of that. And then it says it cannot contain company name, which we've blacked out to protect the innocent, or password. That's pretty standard, right? So I've already kind of gone over, these are all the reasons that this is pretty much wrong. A 10 character maximum is pretty much wrong. If you'll notice, the US keyboard has 94 typable characters on it. So if you remove the 32 special characters, this only leaves 62 possible characters, or 2/3. You've eliminated 2/3 of the character sets that you can use in your passwords just by doing that. I don't even know where that numbers can't be separated thing came from. So I just did a little bit of analysis on this policy, and these are just a couple of the examples of what I could come up with. I guess technically here I could have put the number in the middle, and that would probably have been the best password, sort of looking back on this. But this is basically pretty much the best password I could hope to gain out of this policy. And this is, as you'll see in a little while, is really trivial to crack. So, how do these people make choices? People make choices, I don't know, and a lot of people when I give these talks don't want to admit it, but you can think to yourself and realize that when you're making a choice for a password, a lot of times people will look around them. Say I'm working at, Acme Submarines or something, and I got a big poster on my wall for whatever the newest submarine model is coming out or whatever. I might throw that in my password because I can remember it, because every day I'm at my desk, I can look up and see the submarine poster and I can be like, oh, my password was Submariner 255 or whatever. So that's always common, and so the reason that I know that, I'm not just making that up, the reason that I know that is when we go back to some of those breaches I was showing you, when we're analyzing those breaches, a lot of times I don't know where they came from. A lot of times I'm just trolling Pastebin and I find a big SQL dump from some company, and what I do is you crack about half, 2/3 of the passwords and you start to look in them and you'll see the company name, products the company makes, you know, all kinds of things, and it's fairly trivial to figure out where those hashes came from. And so probably about 1/3 of those databases you saw on there, we've actually had to figure out where they came from. That doesn't work every single time, but 90% of the time I can figure out where it came from if I can crack enough of the passwords. Numbers. Numbers are almost always in a date format. 2 digits or 4 digits. Why? Because it's easy to remember. You know, so-and-so's birthday, you know, the year of Pearl Harbor. I mean, it could be anything, but they're almost always dates. If the policy requires a capital letter, 9 times out of 10, you'll use that as the first letter, because that's how we in English have come up to, you know, that's our language, to put words together. The first letter is capitalized. So that's easy to remember, right? So we do that all the time. And if the policy requires a special character, I almost always see that at the end, because that's the hardest thing to remember is the special character. So you just throw it at the end kind of as an afterthought. So this is kind of a play off the default AD policy. We've already talked about this a little bit. Your policy must be 8 characters, uppercase, number, and a special character, right? Does that sound like a common password policy most people have? So like we were just saying, the average person is going to capitalize the first character, choose a word or a name that's relevant to them, choose a meaningful date, and choose a random special character. And most likely they're going to come up with a password that looks like this. Capital, my name, meaningful date, special character. I can crack 60 to 70% of passwords with just that, with only changing the amount of letters right here and switching this from 2 dates to 4 dates, 2 digits to 4 digits, and changing the amount of letters here. I can crack an infinite amount of passwords. So I threw this in there after some people told me after I gave this talk the first time, they were like, hey, my passwords are leaked, you know? So we're security people, you know, our passwords, although I've cracked quite a few security people's passwords too while I've been out on jobs. But keep in mind that we're talking about average people, you know, I mean, you're talking about 5, 10, 30,000 people that are working at a company, and they're just regular people, and they don't have any education on password policies, and so they basically come up with the bare minimum. You know, have you ever been trying to input a password into a site and this does not meet the policy, this does not meet the policy, and you're like, fuck, and you just keep doing it and doing it. Yeah, I mean, you're doing the bare minimum to get by on the policy. You're not saying, I'm going to use the most secure password possible, because that would automatically work with the policy. I've also noticed that most companies aren't really interested in security. It becomes secondary to making money until they are involved in some sort of breach or hack. So these bad password policies, lazy network admins accepting the Windows default AD policy, badly coded applications like we were talking about before. CEOs complain. I had a company not that long ago where they had tried to enforce a stricter password policy on their wireless, and so what had happened is all the CEOs had come down with their iPads and their Zooms and all that stuff, and they were like, we don't want these freaking certificates on our iPads. We don't want to have to come down and get something more secure every time we get a new toy, and putting in special characters, is difficult. So a lot of times I've found that companies are, IT departments are having to mold their policies based on what the CEOs want, and obviously that's not always the best thing. And I've also noticed that we do pen tests all over the place, but not a lot of companies have regular password audits of their policies and their users. I'm a firm believer that if you audit your passwords, 3, 4, 10 times a year, and every time the same person comes up with a bad password and you visit them, eventually they're going to be tired of getting a visit from IT security, and so eventually morale will improve, so they say. And so anyway, so how can we as pen testers leverage this info in an attack? So I do this all the time. This is not fiction. We can utilize current real-world lists to gain insight. So we'll look at analysis of some lists and how we determine that information. And using all the common passwords out of those lists, we can attack new password lists. And so people, as we know, tend to use the same or similar passwords across all internet accounts. I could name a few people that's happened to, but I won't. Anyway, so here's a little bit about the difference between brute forcing a password, which is basically trying 001, 002, 003. We all know what a brute force is. It's slow, painful, and excruciatingly boring to watch. So here we are back at the 94 typable characters, right? So say we have a password that's 7 characters long, and we got to try 94 different characters. So this would be factorial, 94 times 94. Anyway, if you added that up at 250 million passwords per second, you're looking at 72 hours to brute force a 7-character password. And that's being a little bit generous. And so that's about 250 times faster than John the Ripper. So who knows how long that would take. But what if we knew the password policy, right? So if we knew that the policy, let's go back to that one we were looking at. Say we knew that it was an uppercase character, at least 7 characters, and it had to have a number and a special digit. Well, what if we could just take the character set of the password we were brute forcing and say, instead of brute forcing all 94 characters, we just want to brute force 26 because it's just uppercase. We're fairly sure the first letter is uppercase. So instead of testing 94 characters, we only need to test 26, right? Because there's only 26 letters in the alphabet and they're all uppercase. So that cuts this down to 26. Then we got lowercase 26, lowercase 26, lowercase 26, 10 for digits, and 34 for special characters. So if you add all that up at the same 250 million passwords per second, we cut that down to 6.21 seconds. We can do that entire key space. So this slide's actually about a year old. There's a lot more breaches. I just haven't updated it yet because these are some that everybody's sort of heard of. Here's about how many passwords are coming out of these breaches. The Rocky list, which was probably the most famous about 2 years ago, had 14 million passwords. Then there's the Gawker list, which we're all familiar of. PHPB, eHarmony, and then I can't say the name of this site, sorry. But anyway, I put that on there just because it's interesting to me to see how many places are still using MD5 and DES. I mean, really, DES? And so I like to talk about what we can learn from these breaches. So the interesting thing about these breaches is we can learn the most common password lengths, right? So if most people are using 8-character passwords, we can figure that out. We can discover the most common password character sets. So like we were just talking about, if I have an analysis that says, 30% of the passwords in these 4 lists match a certain character set, that's one of the first ones I'm going to try. And so you saw how cutting your attack all the way down by character set made something that could last 72 hours down to 6.21 seconds. So now what I can do is I can do 10, 20, 30, 40, 50 different character set attacks in the same amount of time that I could have done one brute force attack. And so that's what makes it interesting. What we call a root password is the actual word. We are all familiar with the leet speak, whatever. So this is some neat way to write password or whatever. But what we do is we're only interested in the word itself because in the same way that John does, Hashcat has rule files. So instead of having these big, giant gigabyte lists of passwords, what we do is we cut them down to what we call the root password. We remove the numbers, remove the special characters, remove the case, and just have lowercase words, and then we apply rules to them to do all these types of things. Similar to John the Ripper, Hashcat's just a little bit more advanced when it comes to rules. So I just have to explain this real quick. The way we talk about those character sets in Hashcat is we refer to them as masks. And so a mask basically substitutes whatever the character is for one of these symbols. So if it's a lowercase symbol, it would get a question mark L. If it's an uppercase symbol, it would get a question mark U. If it's a number, it would get a question mark D. And if it's a special character, it would get a question mark S. So you can see in my example down here, if this was the password, this is what it would look like in a mask. The reason those masks are important is that's how we attack those things with Hashcat and OCL Hashcat. We basically input the mask. So this mask would test every uppercase character in this place, every lower in this place, every lower in this place, and so on and so forth, which exponentially cuts the time of our brute force down really, really low because we're not testing 94 in every place. So the other reason those masks are important is that, I'll come back to that, never mind. So here's some statistics. This tool is actually in Backtrack. It's called DictStatPy if anybody needs to see it. It's in the pentest /pentest/wordlist directory. Basically, it's a little Python script. You run it on a word list and it outputs 4 pieces of information, which we're going to go through real quick. The first piece of information that it outputs is the line count statistics. So you can see that in the RockU breach, 20% of the passwords were 8 characters long. I mean, 20% might not seem like a lot, but that's huge to know. And so if you add up 7, 8, and 9, you come up to almost 50%. And so now you know already that in a real world password list that was just compromised, that 50% of the passwords were 7, 8, and 9 characters. So you've already narrowed down your attack surface considerably for cracking new lists. So there's actually, and so you got to put all these 4 pieces of information together, right? So the second piece of information that comes out is the character set. So lower alphanumeric, 42%. So now we know that 42% of the passwords are lower alphanumeric. And so we add that up with our 7, 8, and 9, and we've lowered our attack surface even more. So the next piece of information that it outputs is these masks. Remember we were talking about the masks, and so this tool actually outputs the masks in their percentages. And so you can literally copy and paste these masks out of here and you can have the top 20 attacks against a password list. And so what you do is you keep a running database of masks and you can always figure out which ones, you know, as you keep adding and adding and adding to the database, you'll always know which masks are on top, which ones are the top 20, which ones are the first ones you should attack with, assuming you're keeping your database current, obviously. So here's the output of all 5 of these top breaches put together. And so you can see that 23% are 8. I mean, I won't go through all of this, but you can see the data. And if anybody wants to check out that tool, I'll be happy to show them how to use it. It's fairly simple. And then so once you get all this data together, you can make a conclusion. So, excuse me, the conclusion here is with 8 to 9 using lowercase and digits, you know, with word after digits, we could have cracked over half the RockU list. That's all we needed to know. And that's 14 million passwords. So we could have cracked 7 million of them just knowing that key space. And then so, same thing, these are the masks from the top 5 breaches. So this is me combining all the lists and running the tool on all the lists together to get these masks. And so these are important to us because, like I said, I keep a database of masks so I always know which ones are on top. The tools I use to analyze these lists are, so there's DictStatPy, which is what we used. MaskGenPI basically makes random masks based on some flags and variables. And then PolicyGenPy is a little bit newer Python script. And it basically asks you some questions about what the password policy might be. And you input some answers and it will output you masks that you can use in the attack based on that password policy already. So pretty cool stuff. If you hate Backtrack and think it sucks, you can actually just download the tool itself from here and put it on whatever distro you think is better. So how does all this info help us, right? So it eliminates the need for large word lists, right? The masks can be used, because technically when we're using these masks, we're technically doing a brute force at this point. It's just that we've narrowed the brute force down to just certain character sets in certain spots. So these masks can be used with OCL Hashcat, which is the GPU-based version. They can be used with Hashcat as well. And so the policy GenPy allows us to profile password policies. And so every time we analyze a new breach, we get new info for our attacks. And so that's why I have a group. We have a group of about 10 or 15 solid guys. And so we're always collecting word lists. Most of us, you know, work in the security field, and we don't give out the list or anything, but we will give out some of the research numbers if anybody's interested. So the methodology I use for cracking passwords is the first thing I do is brute force up to 5 or 6 characters, since that's fairly simple to do. The next thing you would do is execute against all your word lists that you had in your repertoire or whatever. And then the next thing I would do is these mask attacks that we're talking about. The next thing I would do is these combination attacks. So what OCL Hashcat supports is what's called a left mask and a right mask. I'll talk a little bit more about it, but it's basically like a left side and a right side type of thing. So it's kind of like, remember in math, what you do to the left side, you do to the right side. So it's similar to that, but you can put different dictionaries, like one dictionary on the left side, one dictionary on the right side. And what OCL will do is combine all those, each word in the left mask with every single word in the right mask, and so on and so forth. And so we call that a combination attack because it combines the words together, and it can be really, really effective. The next thing I do is rule-based attacks based on profiles. I, set up rules based on the password policy and see if I can attack it that way. And then the last thing we ever do is what I talked about last year. Me and the Hashcat guys made up a custom attack we call the fingerprint attack, and it's a little bit too complex to go into right now. But if anybody's interested in that, I got a video on how to execute it and stuff. But basically the fingerprint attack works without a word list. It basically cracks the list, expands it, then puts the list on both sides, cracks it, expands it, puts it on both sides. And by expanding, I mean something similar to what John the Ripper does, where it mangles the rules, where you put in a word and it mangles it and comes out with like 50 words. It's similar to that, but it's a little bit smarter than that. I'll throw this in there. This is the first year Crack Me If You Can contest. The reason that I think this is interesting is because you can kind of see, like, here we kind of had a slow time getting started. What happened at this point is we were cracking just a few passwords, and what we were doing was looking in those passwords for patterns. So there was, in this contest, there was 58,000 hashes released, and it was basically whoever could crack the most of them won. Well, I know that there's no way they just came up with 58,000 hashes somewhere. So what they did was they took a list of words and they ran them backwards against John rules and created these giant password lists. So the first thing I knew is that most of these hashes had been created with a rule of some kind. So the first thing we did was open up the passwords and try to figure out what the rule was. So as you can see at this point, we figured out some patterns and we rocketed it up to here, and then we hit another plateau, and then we had to go back and reanalyze the words and figure out some new rules. And so none of this was done with brute forcing. This was all done with trying to figure out the rules that the patterns in the passwords and how we could reverse them so that we could reattack the passwords using those masks that I showed you. So we're using the GPU now to crack passwords. It's been around for a couple of years. It's kind of old news at this point, but the advances in GPUs have actually come a long way. Even since I made these slides, we're now up to, I think my ATI 6990s have about 530 or 560 cores. And so if you think about it, your computer at home might have 4 cores or 8 cores or even 16 if you're really balling. But so those cores can only do a limited amount of threads per process. And so the long and short of GPU password cracking is more cores, more threads, more cracking. It's really simple. People always want to, I'm going to come back to that, I guess. So there's 2 major vendors for GPUs, Nvidia and ATI. Most people are probably pretty familiar with those cards. Like I said, I probably got to update these slides a little bit. The top of the line ATI card right now is the 6990, and it costs about $600. And so people always ask me what's better. And so I used to be a big Nvidia guy, and now I'm more of a both kind of guy. They both have different applications. Nvidia's significantly slower when it comes to cracking passwords. However, CUDA is much more well-maintained code. They have a whole team of developers, they pay them, they're on top of things, they answer questions, and they answer emails. The other better thing about NVIDIA is using the CUDA software, it can take large lists of passwords much easier. So like my NVIDIA box won't even blink an eye when I dump 10,000 passwords into it. But now ATI, on the other hand, is significantly faster, almost 5 times faster. However, the ATI stream code is shoddy, to say the best, and may or may not work at any given time. and is also really late updating their drivers. However, it is quite a bit faster. The other bad part about ATI is that it doesn't take large password lists. So I now actually have 2 different boxes. And so if I want to do, 5, 10, 20, 30, domain cache credential hashes on a pen test really quickly, I use the ATI box. But if I want to dump 7,000 or 8,000 hashes from a domain controller, I use the Nvidia box. So there really isn't one is better than the other. It's what is your application at this point for that type of thing. Here's just some statistics. Like I said, this box is still in existence. This isn't mine. This is my friend Dead One's box. He's got 8 ATI 6970s in it. But so these are just some speeds that he's getting. See how we have single hash mode and multi-hash mode. So with the ATI stuff, we have to differentiate between the two. But you can see that he's getting 45.1 billion per second MD5s. And so in order to brute force the entire length of 8 key space, it would be about 1 day, 16 hours. So that just shows you how ineffective an 8-character password is. And so you would multiply that by 8. So even a 10-character complete brute force would be a little bit less than 10 days. Oops, hold on. How much time do I got? Oh. Anyway, so like I said, word lists, bigger's not better. I used to have giant word lists and think they were really effective, but now I've decided that those root word lists like I was talking about and masks are a whole lot more effective. Also, I don't know if anybody's ever tried to open up a 4 gig word list on a computer. It turns into a disaster. So I've decided it's much more effective to use these small lists and maintain rule sets. And so Hashcat comes with tons and tons of rule sets. I'm pretty sure we've written about every rule there is to write, but there are some more you can do. We actually wrote some rules. I don't know if anybody's familiar with that Steve Gibson GRC security dude or whatever his name is. And so he wrote a blog post not that long ago about how password padding was effective. I don't know if anybody read that, but so password padding, he was saying that rather than having a 12 or 13 character completely random password, he was saying that password padding, which basically means taking your password and adding some infinite amount of, pattern to the end of it, would be harder to crack than the random password, but it's really not. So some of the examples he had were like his name and like, dot whack, or some other pattern. So we wrote a counter blog post and we rewrote a bunch of rule sets so that his crap's ineffective now. Anyway, so I already talked about this a little bit, but people always want to know. The one thing about OCL Hashcat is it's a little bit confusing to figure out how to use it in the very beginning. So I just like to go over it just a little bit, and I'm happy to talk about this with anyone if you have any more specific questions. This is what I was talking about by a left side and a right side. So you can see that here's a dictionary on this side and here's a dictionary on that side, right? So here's just some example. Here's dictionary 1 with these passwords, and here's dictionary 2 with these passwords. And so the combination attack would create all of these passwords. And so obviously there's only 5 in this list. It's an example, but if you had a couple million in your list, or even 10 million or whatever, this can turn into a giant password attack. But it can also be really, really effective, right? Because you get stuff like 1, 2, 3, 4, 5 angel or whatever. And we all know people love to put 1, 2, 3, 4, 5 at the beginning or the end of their password. So here's some more examples of the way that it works. So basically you can use the masks or a dictionary on the left side or the right side. So this is the confusing part, but once you start working with this a little bit, it really makes a ton of sense. So like in this example, we have our dictionary over here, and then we have a couple of masks on the right side. So dictionary masks. So what this would do was it would take every word in the dictionary and it would append 2 digits to the end of every single word. So a lot of our password lists, like we might have every single word with 1, 2, 3 or whatever. We can get rid of that whole giant crappy list and just do this and append 2 digits to the end. This is a similar example where it would prepend 4 lowercase characters. So now we've switched our dictionary to the right side and added our digits to the left side, our mask to the left side. And so now we have 4 lowercase characters in front of every dictionary word. So that can be effective too. And then in the last example down here, what would you do if you wanted to make lowers and uppers here, or if you wanted to do the entire key space here? Then what you can do is assign a variable, just like if any coding whatsoever. So you give it a -1, and you assign all the variables that you want to be in that -1, and then over here on the left side or the right side, you just use 1 instead, and then it will take lower, upper, special digit all into account. So that's sort of the 2-cent version. Like I said, if anybody's more interested in using this stuff, I can definitely talk about it more later on. These are just some quick examples of some of the rules. So all these attacks can also take rule files. You can also pass the rules on the command line. There's a K and a J. I think I have an example so you can see, but there's a K and a J to pass the rules to either the left side or the right side. So you don't do the same rule on both sides unless you want to. These are just some examples of the rules. These are real similar to John the Ripper rules. I think they're actually the exact same format. We try to keep that stuff the same so that people coming from John the Ripper to Hashcat can figure out that the rule set fairly easily. I got one more slide of rules. Yeah, and so some of these, I don't know if I have that. There's about 10 or 20 Hashcat specific rules that don't work in John. I don't think I have that slide up here anymore, but this is all on my blog and Dead One's blog, and so you can look at all these rules and see just all the ways that you can manipulate a word just with the rule set. And like I said, that's nothing new and groundbreaking. They've been doing it in John the Ripper forever, but some of the new rules are a little bit cooler. Here's some examples of doing a rule. So J applies this rule, which is uppercase the first character to the left side. So here we're uppercasing the first character in dictionary 1, and then we're appending 2 uppercase characters to the end. J does the rule to the left side, K does the rule to the right side. So here you see we capitalize the first letter of each word in dictionary 1 on the left side, and capitalize the first letter in dictionary 1 on the right side. And then there's now a new cool tool called OCL Hashcat Plus, because the biggest complaint about CUDA and OCL Hashcat was that it couldn't use a word list. You had to do something to make it use a word list. So before OCL Hashcat came out, it can take a straight word list. And so before that came out, what you used to have to do was you used to have to do a dictionary on one side and append a digit to the end, and then create a rule which removed the last digit at the end. So if you want to use word lists with OCL Hashcat, you have to use this format here. It's sort of a trick. So what happened was OCL Hashcat Plus came out. So there's no left and right side to OCL Hashcat Plus. It's basically just word lists and rules. It has a bunch of new algorithms. When I first did this slide, the biggest new algorithm was MD5 crypt. There was no GPU-based MD5 crypt password cracker. Since then, DES has been added. When Gawker list came out, everyone was looking at each other like, oh, where's the DES GPU cracker? Nobody had one. So one got written. This year, the Crack Me If You Can contest came out. The guy that runs it, Rick Redmond Minga, is actually a good friend of ours, so he knew what algorithms weren't supported. So he made a bunch of the hashes in the contest, like MS Cache version 2, I mean, really? And so those were worth the most points because he knew that we didn't have a GPU cracker for them. But Adam, the main developer for OCL Hashcat, surprised him and stayed up all night and wrote one. You know, so now MS Cache version 2 support is in there if you need it. Also, the coolest, newest thing is it now supports WPA. So I don't know if anybody's familiar with WPA cracking, but Pirate used to be the main tool for WPA cracking. It was, you know, the de facto standard tool, and it's a great tool. However, the way I understand it, the way that he used PY CUDA instead of actually using CUDA itself, there were some limitations on speed, and so that's been rectified. The only stats I have is that I have a box with two ATI 6990s in it, and it was getting about 120,000 passwords per second with Pirate, which WPA is significantly slower, but so that's quite a few for WPA. And with the new version of OCL Hashcat Plus and WPA, I'm getting about 350,000, so it's about 3 times faster. There's several other algorithms.
The MS Cache V2, is that code actually released publicly already? And what kind of key speed are you getting? Because with Kane, I'm only getting like, I think 70 a second.
So we're getting 4 million per second is the fastest we can get.
Awesome.
So it's still very, very, very slow. But anything helps when you're, when you're trying to get a key. So I think the last time I checked, it was 4 million per second. So just real quick, here's the OCL Hashcat Plus example, kind of like those other ones, but this obviously would be all one line, it just didn't fit. So M is the mode. If you just do the help, it'll tell you all the different modes. Modes is basically what algorithm we're cracking, the hash file. N is sort of a fine-tuning speed for GPU. Then R, there's, inside the rule directory, there's all the rules you want. We release all this stuff publicly. Nobody's hiding any rules. They're all in there. Best 64 is one of our custom rules. We even stole the Russian people's rules. It's in their password pro rule. I mean, then there's the output file, and then you basically just give it a word list. Or the really cool feature that we implemented is that if you want to give it every single word list in the directory, you can give it the old star, and it will go through every single word list. The last tool that came out was OCL Hashcat Lite. It's the same as all the other ones, but it's optimized for single hash. So it's about 2/3 faster than any of the other ones, but you just pass the hash on the command line. And so it's really for single hashes. It basically started for DES and the Gawker hashes, but it's basically the fastest tracker for any of these hashes. The thing is these are all the ones that I was starting to see on pen tests. And so it didn't used to support MS, and this support is all now in the OCL Hashcat Plus too, but I was seeing Microsoft SQL, DES, Oracle, all on pen tests all the time, and none of those were supported, so those are all supported now. Here's just a little, this is actually supposed to be billion per second. I don't know, but this gives you an idea. John the Ripper on a quad core can do like 3.8 million per second. OCL Hashcat Lite with those 3 HD 6970s could do 115 million per second. So that's a significant improvement. And so 6970 is not the top end card. So those are a little bit lower end, more affordable cards, but still really, really good speed. So I always like to finish this up by talking about the solutions. What can we do to prevent some of these attacks? Obviously, I like the way it is because I like to crack passwords. But so if you're at a company and you want to know how you can improve your password policy, the number one issue I see is web application passwords. It's developers that either don't know how to properly sanitize password fields, and you get like what we saw there in the beginning, no special characters. A lot of times it's application developers that are under a deadline, and the security of the application becomes secondary to the functionality of the application because they got to get it going. Regular audits of company password policies. I'm a big advocate of this. I've helped a few companies build password cracking, rigs so they can audit their internal password policies. Obviously, doing that by a third party can be sort of hit or miss, but doing it internally by your security department can be a super, super big plus. Obviously, more sophisticated password policies, and what I mean by that is getting away from what I was talking about. Like, make your rule say, instead of making, if it's not that hard to make a rule that says the name of the company can't be in the password, it would be absolutely trivial to make a rule that said the first character of the password can't be uppercase and the last character can't be a special. All the numbers must be separated, for example, so you can't get dates in there. I mean, all these things would be fairly trivial to implement into a password policy. Web applications, again, so increase minimum password length complexity. I mean, there's nothing better than a longer, more complex password. Longer and more complex. The longer you can get it, the better you can. I used to advocate passphrases a lot, but since then I've learned a new technique where I actually go to the Ubuntu on the website where they house all the IRC chat logs, and they're nice enough to keep those all in a text file format. And so one of the newest tricks that I've learned is I go to that website and I download every single text file with wget. It's still old school, you can download the whole site with wget. And then I take every single one of those text files and I'll remove the timestamp and the username. And now what I have is a list of passphrases with spaces and everything. And they're phrases that people are using every single day in multiple languages. Ubuntu has like 1 million IRC channels, and their chat logs go all the way back to like 2008 or 2007 or something. And so I now have, you know, gigs and gigs and gigs of passphrases, and I've gone back through all my old lists and cracked an insane amount of passwords with those lists. So passphrases are not always the best thing in the world when people like me figure out where to get those phrases, you know, because if you think about it, people in IRC are using slang, you know, real world phrases, all that kind of stuff. They're talking like they normally do, and those are the kind of phrases that they would input for a password. Web-based solutions, I mean, every time we get a web application at work, I'm always disgusted to see that the hashing algorithm in there is fairly poor. MD5 or DES or some other failing algorithm. Some of the newer applications that are not getting hacked and doing better are using bcrypt or blowfish or some more complex algorithm. You know, complain when the policy's bad. You know, don't be a dick. Go to your IT group and say, hey, this policy sucks. I just saw this guy Martin talking about password policies, and we should maybe change this. You know, obviously two-factor authentication, big deal. You know, go to two-factor authentication for web-based solutions. And then I can't even believe that people still have LM password hashing turned on when I go places. I mean, I literally can't believe it. And especially when you say, hey, is there some reason this is on, like some like ancient legacy application in the, you know, back closet that's running on the internet? No, we just didn't know. You know, we didn't like it. So that just shows that there's not a lot of education out there about password policies. And the last thing, this is terrible. We have rules that account for this as well. I've read some posts where keyboard walking, like QWERTY, you know, right across the keyboard. Like, in case anybody was wondering, QWERTY was the most popular password in the entire Gawker password list. You know, and that's called keyboard walking. You know, dates, years, all that kind of stuff is trivial. I mean, like, we just assessed an application recently where the default password made like a V pattern or something on the keyboard, trying to be tricky instead of going straight across it. So what do? The next thing we do is we write rules for every V and X pattern I can think of on the keyboard, you know? I mean, that's all that happens is your policy gets out, somebody writes a rule for it, and you're pretty much fucked. All right, so if you think this stuff is cool, where can you learn some more? We got a ton of articles on my website, questiondefense.com. There's a ton of articles on my friend Dead One's site, obsecurity.info. On the Hashcat site, there's like a manual where we try to put it together to teach how to use some of this stuff. Want to really thank Adam, who's the head developer of Hashcat, Dead One, and then my good friend Alex, the KY Killer. And then if you think I'm an idiot and you want to complain, you can email me here. And you can also yell at me on Twitter here. Thanks. Does anybody have any questions? Does anybody have any questions? Yes.
How effective do you find a good solid salt added to, say, an MD5 affects your ability to track those?
So it just depends. That can depend. So there's a ton of different MD5 hashing algorithms, and the thing is that whether some of them you need the salt to crack it, and some of them you don't. Some of them the salt is actually hashed in with the password and can be reversed. It can be effective, but MD5 as a whole is a fairly weak algorithm. And it's also, how easy is it to get the salts? If you're salted with a username, for example, if you're salting your passwords with a username and the entire database gets compromised, the attackers already have the username, so it becomes ineffective. If it's if it's a large company where you could enumerate a ton of email addresses off the internet, for example, and we see that the email address scheme is like mboss, like first letter, last name, which is common or whatever, the next thing I'm going to do is create a brute force list of, I can go to Skull Security Ron's site and I can get the Facebook name list, and I can append one letter, to the beginning of every name on there, and then I can run a brute force with salts as well. So that's one thing that I didn't show in here is that OCL Hashcat can also take a salt file. So if you don't know the salt of the password, you can create random salts or names or whatever, and you can put those in the salt file, and it will utilize those as well. So it's all on the availability of the salts, I guess.
the what would you say is then a reasonable password length? Like, you know, obviously you start making policies so complicated, you're calling the help desk group and sky, nobody can remember. You constantly reset.
I mean, I always hate to give, because this would purely be my opinion, but I think over 14 characters is a must and fairly randomized. I mean, you don't have to make it totally ineffective. A lot of times, like, you can take a passphrase, make sure the spaces are in there, and then think of some rule, like reverse every word and capitalize the third letter. You know, it's all up to, you know, the individual or the company. And then, I mean, I just like to, you know, I mean, I understand large password policies are a pain, but would you rather have, you know, a bunch of help desk calls, or would you rather get hacked and be on the internet? I mean, you know, it's sort of the way that I kind of put it to people.
Yeah.
Does the GPU stuff work in a VM?
No.
So if you're running from the VM, you have to be running from the host system to even touch the...
Yeah, so virtualized stuff is still not far along enough. You know, we've gotten to where we can use the wireless card, but it's the same reason that an internal wireless card comes up as a wired network in a VM.
Yeah.
Same, it just can't access the physical hardware in the same way.